Welcome everybody. So last talk, in the last talk, we discussed about characteristic, properties, no, examples mainly. So I hope everybody understood the talk. Now I will proceed here. So today we will start with theorems. We are now going to definition. We are going from definition to theorems now. Okay. So here comes our first theorem or result or proposition, whatever you prefer. So theorem. What is our first theorem? You take every field, any field, okay? Let F be a field, any field, then F contains a subfield isomorphic to either Q or FP. Sorry, FP, by FP we mean, what is FP? In ZP, sorry, the Z mod P is FP. Z mod PZ. Okay. So in somewhere FP is actually this. In some book it is written FP. In some book it is written ZP or Z mod PZ. That's same thing. Okay. So whenever I will talk about the FP, you mean I am talking about ZP or Z mod PZ. That means F2. What is F2? F2 means 0 bar 1 bar. What is F3? F3 means 0 bar 1 bar 2 bar. Okay. So we need to prove this. We will prove by characteristic, the property of characteristic, prove by characteristic of F. How the proof goes on? So proof. So first of all, we are considering the ring homomorphism. Consider the ring homomorphism from, consider the following ring homomorphism. What is the ring homomorphism? Phi. We are defining a homomorphism from Z to F. Okay. What is the map? By phi of n. So goes to n 1 of it. So by ring homomorphism, in case you forgot, so if A and B are two rings, then if B is A or B, if A or B are two rings, then if it is a ring homomorphism, A to B is a ring homomorphism if A f of A plus B. So this plus is in A. Here we are two rings, so there might be two additions equal to if A. This addition is in B. B. A product in A. B equal to if A product in B if B, and obviously if 1A, it will always goes to 1B. Okay. So the three properties that will satisfy is called a ring homomorphism. So I will just by seeing you can say it is a ring homomorphism. Verify it is a ring homomorphism. So obviously fields are rings, so you can say about that ring homomorphism part. Okay, let me write this properly. It is phi. Okay. So this map has a kernel here. What is the kernel? Consider kernel of phi. So kernel of phi, that means all those n belongs to z such that n into 1 dot f equal to 0 of f. Okay. So I will sometime not write 1 of f. 1 of f means 1. 0 of f means 0. So what is kernel? There is 1 of f. Now there are two cases. So this is precisely, you can say, set of all integers that yields 1. So 1. Whenever one is same, I talk. So better it is said, not said, it is subrings. Now, so we say that that kills 1. So there is a obviously matter of characteristic, because where 1 is killed, there is also always a matter of characteristic. So there are two cases: either one characteristic is 0 and characteristic is finite. First case, what is the first case? Let characteristic of the field F, that is 0. Okay. Then see, if characteristic is 0, then no positive integer will kill 1. You cannot say 2 into 1 is 0. Then the characteristic is 2. At least 2. At least 2. Smaller integer might work. Okay. But characteristic will characteristic is 0, so no positive integer. If any positive integer other than 0 kills this, then that will be the characteristic. But characteristic is 0, and characteristic 0 means no positive integer will kill other than 0. Then kernel of psi, it will be singleton 0 or 0. So by the first isomorphism theorem, z will be z by z quotient, kernel is 0, so z by 0 isomorphic to phi phi of z. That means z, which is isomorphic to phi of z, that will be contained inside F. Okay. Now see, whenever Z is embedded, embedded means an one-to-one map. So that is an one-to-one map, Z and phi Z. They are isomorphic. Then Q is already inside F. Why? Because Q is the smallest field containing Z. Okay. And this is C. This is the smallest field containing Z. And F is arbitrary any field containing Z. Containing Z means containing an isomorphic copy of Z. Isomorphism does not hamper the algebraic properties. You already know. So doesn't matter. Whatever will be Z or Z. Why? Why? If Z inside F, take A comma B belongs to Z with B non-zero. Okay, then observe that it is a field. F is a field. So F will obviously be respect division. That is Q is inside. I mean, what I am trying to say here, that if you take suppose 3 or 4 belongs to Z and Z is inside F with isomorphic copy. So then F is there. So that means 3 and 4 will be inside F, but then 3 by 4 is also inside F. So in this process you can take any two numbers and give their quotient, they will be always inside F. That means in Z that gives Q. That process doing this process gives you Q. So Q will be there. Okay. So that proof is complete for the case one. We are about to show that it contains Q or FP. So that is Q. Q content there. Isomorphic copy means if I take 3 and 4, so there will be some isomorphic images there. Okay, that image. Next, what happens if characteristic of Z is P? If uh, and we are done. Characteristic of F is prime number. I have previously said in the last talk that characteristic of a field is always a prime number. So if it is P, then what is the kernel? Kernel of phi? It is ideal generated by P. Okay, that is the thing. Characteristic is P. So why it is P? Because P will be, so because P is inside, if P is inside kernel of phi, and obviously P is the smallest. P is the smallest such thing. So if any other things Q kills one of F, then suppose Q equal to PA plus B, then you can say that P by discarding uh, I'll do. Why it is kernel? Let me see. Let me explain elaborately. Trivially, P, the thing P is inside the kernel of phi with P smallest. If Q is any other integer that yields 1, then by division algorithm there is a then by division algorithm. So Z is a Euclidean domain, so I can perform division algorithm. Q equal to PA plus B, where I know the remainder will be either that is the remainder, B is the remainder, so that will be B. Okay. Now it kills one, so passing through 1F or multiply. So we'll do one thing. This is an integer though. So we can apply phi of both sides. Implies phi of Q equal to phi of PA plus B. That will be the nothing but that will be phi P phi A plus phi B, because it is a ring homomorphism, which implies that, but phi Q is Q into 1 of F, that is A into 1 upon F, P 1 of F plus B 1 of, that is the thing. Okay, if B is non-zero, then okay, in different way. Now I have seen, I have assumed that both P and Q kills 1F, so it is 0 equal to 0 plus B into 1 of F, implies that B is smaller than P killing 1. Okay, which is a contradiction because I assume P is the smallest. Okay, which is contradiction if B non-zero, because it is non-zero side, it is 0 then. So B must be 0 and Q equal to PA, which means Q will be inside the ideal generated by P. That means kernel of psi will be inside ideal generated by P. So psi is exactly ideal generated by P. Understand what I am saying? So I have done the proof here in this case. So kernel is this. Again, I will apply the first isomorphism theorem here in this case. By first isomorphism, Z mod pz is isomorphic to again phi of it is it is so Z mod pz embeds so contains Z mod pz because it is a field here, so it contains an isomorphic copy of this thing, and this is a field. And contains a subfield isomorphic to Z mod pz or fp, what I wrote there, and we are done. Okay. So this is the proof. Very elementary. I have worked out each and every details of the proof. Okay. So see this, and if there is any mistake, please let me know. I might be doing something wrong, or there might be some typos. Don't confuse and inform me if there is something. Okay. So let me go to the next thing. What what is the definition of prime subfield? Prime subfield means, okay, I will tell during writing. The prime subfield of a field if is a subfield of if that is generated by multiplicative unity, that is generated by 1f. Okay. That is generated by 1f. So what we have so what we have did here, we have done here. So it is from there I can say that the prime subfield is either isomorphic to U or Z. Sorry, Q or the isomorphic, sorry, either prime subfield is either isomorphic to uh, let me elaborate, isomorphic to either Q or ZP. That is the thing we have did there. Because the kernel was in the kernel, you can see this where I have did the proof in kernel. Okay. I will give you also hint. Don't worry. The prime subfield I need to write in another font. The prime subfield. So if characteristic of f is 0, then prime subfield isomorphic to Q. Why? Because then, acha, why it is isomorphic to Q? See, then Q means quotient of two Z. One or my one thing is quotient of two elements from the integer. So any integer A is A into one model one, and B also B into one of A, B non-zero. So it is a subfield. So I can divide them. Subfield means division also permits. So in this way you will get Q. You endlessly, I mean, add elements. Okay. So for example, how to suppose 5 by 6. Okay. So I can add one 5 times. 5 times. So I will 5. I will add 6 times to get 6 and divide them. That is characteristic 0. Okay. So any element I could generate by that adding that type of element. If characteristic of f is p, then the then its prime subfield. Then the prime subfield isomorphic to ZP. Okay, because if you add 1 p times, you can get elements 0, 1 bar, 2 bar, p minus 1 bar by adding. So how to get p minus 1 bar? So it is adding p minus 1 times of 1 by f. 1 above this we cannot get. ZP will be inside there for sure. And this is the smallest subfield. So prime subfield is the smallest subfield. Okay, I think you get this example. Prime subfield of Q or R C. It is. What is this? It is Q. Because it is a characteristic 0. Okay, it is a characteristic 0. And characteristic P, if f equal to ZP or ZPX. What is ZPX? It is the rings of, or sorry, it is a fraction field of all polynomial. So then, yeah, subfield is ZP. Because in ZPX, see, in ZPX, the polynomials doesn't matter. Only matters the scalar thing, 1. So if you add 1, you will get same ZP things. Because AX, X square, that don't matter here. Okay, we need only to consider 1, which is a scalar. So that will also be ZP. Okay. Next is about the field extension. definition of field extension. If K is a field that contains another F, then said to be field extension. That means if that is written in this way, notation. A is there, F is there. That is the notation. So it is a small field, it is a large field. That is same thing like subset and superset. It is subfield and it is superfield. So it is the superfield is called the field extension. Denote it by K. It is denoted by this. Okay. So if you can see this, observe that every field F is an extension prime subfield. Okay. Because it is actually it is the smallest subfield I told you that contains F. Inside F it is the smallest thing. Okay. So every field is an extension of its prime subfield. That is the thing. You can easily examine this because you take one and generate the field. So you will get the prime subfield, which is contained in F because F is a field. So that field, if you take calling that F1 prime subfield, that will be an extension. That will be F will be extension of this. So if you just remember the properties of vector space, but the definition of vector space and see that extension A over F, K can be considered as a vector space over. So you can see that it satisfies all the axioms of the vector space. That means sum of two elements of K will be there It is trivially because it is a field. More precisely, the scalar multiplication, left multiplication, right multiplication, the distributive laws, all will be there. It is a vector space. So as soon as I pronounced the word vector space, there will be a matter of dimension. Okay. What is the dimension of the vector space of K over F? That is a very important concept. That is that gives me another very important definition. It is called the degree of extension. Right? Yield extension. The dimension. I will come into the examples. Don't worry. Is called the degree of extension. And what is the denoted by? It might be finite, it might be infinite. Okay. It might be finite, might be infinite. For example, example. What are the examples? C over R. C is a subfield. C is a subfield. R is a subfield of C. C over R. C. Complex number, huh? C. C equal to R plus, that is C is generated by, right, because in the element A plus Bi you can take one. A is coming from I and one is B is coming from I, so degree of extension is 2. What is about, if I take Q adjoint omega? Okay, let me, we will come this later. What is Q adjoint square root of 2 by over Q? So it is a bigger field, it is smaller. So it is a field extension. So what are the vector space dimension? If you consider Q root 2 as a vector space over Q, then what are the bases? 1 and root 2. Then It is also there. Okay, these two. See, the reason behind this is I am writing here. So what are the elements of Q plus A plus? So it will look as, because take any element X belongs to Q. Then X will look like how? A plus B root 2 by C plus D root 2 by R C D. Okay. So field means the quotient of two things will be there. Now multiply the by the conjugate thing. That is C square minus 2D square A plus B root 2 C plus D root 2. So that will be C square equal to 2D square C plus 2PD plus root 2 into BTC. So it is from Q. This thing is from Q. So the whole thing is an element. The whole thing is an element from Q plus root 2 into an element from Q. So it is defined by generated by 1 and root 2 over Q. You are understanding the things. So see, it is finite. I am giving example. It is finite. It is finite. It is finite. So infinite field extension. What could be an example? So finite extension means the degree of the vector space K colon F. What I have defined here. That is finite. That is fine. If this is finite, then it is finite extension, and if it is infinite, then it is infinite extension. Consider these things. Then, okay, this is an infinite extension because you are attaching all square root of primes. So if it is finite, then it is generated by only finitely number of primes. But we know the number of primes is infinite, reason the there is a reason, and any prime and be. Okay, you do this of your own. I will not tell this. If you not, if you are stuck, then I can help you in this thing. This homework. I will tell you later. It is q over pi. It will. What is the q over pi? Let me write it here again. Polynomials in pi. That is a0 plus a1 pi plus dot plus a in e in y over m, where ai bi belongs to q or all I, and denominator. So then that thing. That is non-zero. That means the coefficients are non-zero. So there is an infinite extension because you cannot generate it. Suppose it is finitely generated, then you will get a finite basis. But the higher powers of pi, because pi is a transcendental element, cannot be generated by the smaller things. Then it will be algebraic over Q. That is the main thing. Okay? That is the main hunch of this thing. So let me close and conclude this class.